Hey everyone, welcome back to Hangar Negative 1. I'm Izzy Benavi, and this is Improvised Dynamics. Many of us love to go camping, and it can be a really fine thing to unplug every once in a while and commune with nature. However, it can be really advantageous to have access to electricity when you're out in the wild. So with that in mind, the aim of this project is to show you how you can build your own off-grid solar power station. I designate this Project Ra, after the Egyptian sun god. Now, whatever. Anyway, the aim of this video is I'm going to introduce the project and then go over a little bit of the theoretical development and then finish up with part selection and testing. Now, I understand that it can be cheaper and easier to just go out and buy a gasoline generator. However, this is my project and I wanted to build another solar power station, so bite me. I intend for Ra to be a freestanding structure that can be used for shade outdoors. The scope of this project will cover the selection of components, the design and construction of the shelter that will hold the solar panels into such a position where they can effectively throw shade, and a weather-resistant enclosure which will house all the guts and keep the elements off of sensitive electrical components. What I want out of Project Ra is, at the end of this summer, to transport it 1,000 miles into a dusty, windy, hostile environment. Build a freestanding shade structure in situ and have it provide the power that I need to power the devices that I've chosen. Think we can do it? I do. Let's get started. So what goes into a solar station? Well, at the center of our entire system is the photovoltaic cell. This is the solar panel. This is the device that transforms solar radiation into electricity, frequently in the form of DC or direct current. This panel outputs 12 volts DC. However, that's a nominal voltage, and its output can vary, depending on the lighting conditions, anywhere between 0 and 17 volts. So we're getting voltage out of it. That means that we can just hook our load directly up and get power out, correct? Well, yes, but like I said, the output of the voltage can vary depending on the input of the light. So if you have very little light coming into it, then you'll have very little power coming out of it. Maybe not quite enough to run your device. So we're going to need something to maintain a constant power output. And that's where we get the battery. However, dumping wildly changing power directly into the battery isn't necessarily a good idea either. So we're going to need a device here in between to regulate the power going into the battery. And that's the charge controller. Now there are two commonly used types of charge controllers that are on the market today. There's pulse width modulation, or PWM, and maximum power point tracking, or MPPT. Now PWM works by rapidly switching on and off the charge voltage to control the input power. Alternatively, MPPT works by balancing the charge current and power to gain the most efficient charge. Now, I actually have no idea how this works, but I've been told that MPPT is basically better in every way as long as all of your panel wattage is exactly the same. We've got a power source. We've got our battery to maintain a constant output. We've got a charge controller to keep from killing the battery. Now can we hook up our load? Well, yes, but the output is going to be DC, so we can only use DC appliances. So we're going to need another device to transform that into AC power. And that is the inverter. This is the machine that converts the DC output of the battery into the AC output that our devices expect. There are a few different types of AC inverters. For this project, I plan on using a pure sine wave inverter. From what I understand, it's a little bit more expensive, but it will yield a better quality output. So now that we've got our power input, our battery to maintain output, the charge controller to keep from killing the battery, and now the AC inverter to flip the signal into what we need, now can we plug in our stuff? Well, yes, but the DC side of this is going to need a little bit of moderation because DC power can get a little bit hot and bitey. And unlike AC, it never lets go. So we're going to need some control checkpoints along the DC side of this in the form of fuses. Now, everything is a fuse in that anything can fail in a circuit so catastrophically as to open that circuit. However, it'd be really nice to control exactly where and when that failure happens. So, inputting a fuse in between each of the DC side components should mitigate a lot of headaches. Now that we know the different components that we need, we can select each one based on our expected power draw. The first step to figuring out how much power we need is to list each of the components that we plan on using on this system, how many watts each device uses, and an estimate for how many hours we plan on using each device. We can multiply those two values together, and once we have our watt hours for each device, we can go ahead and add them all up to get a total system power draw. Now, accounting for some 30% inefficiency in the system, I estimate my total daily power draw to be about 1,057 watt hours. And once we know our expected daily power draw, we can figure out how much panel we need to provide that power. We're going to want enough panel wattage to replenish during the daylight hours all of the power that we've used during an entire 24-hour period. Now, I estimate about 4 hours of useful daylight during the daytime, owing to changing light conditions, cloud cover, dust storms, things like that. So we can take the 1,057 watt hours that we calculated earlier and divide it by that 4 hours of useful daylight to get about 265 watts. So we're going to need about 300 watts worth of panel. Now, I got a package deal on 4 100-watt panels, and when I wire them together in parallel, that'll give me up to 400 watts max. And that should be well clear of the 265 watts that we calculated. With our solar panels chosen, now we can select our charge controller. To do that, we need to know what kind of current we're dealing with. We have 400 watts coming into a 12-volt system. And per Ohm's law, wattage divided by voltage is current. So 400 watts divided by 12 volts equals 33.3 amps, which means we're going to need at least that for our controller. So I'm going to select a 40 amp controller of the MPPT variety that we discussed earlier. Next comes the battery. We're going to need it to store enough juice to feed our established electrical appetite. Going back to that 1,057 watt hours and dividing it by the 12 volts of the battery, we're going to get about 88 amp hours. Now, expecting a battery to be about 80% efficient means we're going to need 110 amp hours. I'm going to go ahead and eat a little bit of the margin here and get a 100 amp hour battery and hope I don't run out of power in the middle of the night. Finally, for the inverter, we just need to add up all of the wattages from all of the devices that we listed earlier, and then choose a unit that exceeds that. Except that I have about the budget for a 300 watt inverter. So that's what I'm going to be getting. Unfortunately, I have about 340 watts worth of devices that I want to use. However, I don't plan on using them all at once, and in reality, I'll probably only be drawing about 140 to 200 watts all at once. So with a little air traffic control, I can keep my power consumption well under that 300 watt maximum for my system. With these specs in mind, we can now just go online and shop around for the exact models that we want to use. For Project Raw, I basically chose these components based on Amazon reviews, so I have no idea how it'll actually work for me out in the field. It could all blow up in my face, I don't know. That being said, I should probably put all this stuff together and see how it works for me in the lab under ideal circumstances. Before I even touch tools, I should probably begin by donning my safety glasses. Thanks, Izzy. AC and DC are different ways of transferring electrical power. Alternating current, or AC, refers to voltage alternating polarity over time, because it's typically generated by spinning a magnet across a stationary wire. The reversals of magnetic polarity accompany reversals in electrical current. AC can readily be transformed to higher voltages to avoid losses in power lines. In North America, AC power frequently comes across at 120 volts, alternating 60 times a second. Direct current, or DC, refers to a voltage that is ideally constant over time. Without ever crossing zero like AC does, DC is always on. This makes it great for constant signals, as frequently used in electronic devices. DC voltages tend to be lower, like 3.3, 5, or 12 volts, sometimes going up to 24 or 48 volts. 40 amp inline fuse on a 10 gauge wire. Given that AC and DC are two vastly different technologies, I figured it was important to at least give a bit of treatment in this video. The difference certainly affects how and why I'm building this project. In fact, because of the gulf between AC and DC, Tesla and Edison would go rounds about which is superior. Certainly each method has its advantages and ideal applications. Although Tesla was the better inventor, and Edison was kind of a shit-tier human being. Battery, 12.9 volts. Okay, and then... Alright. I've hooked everything up and tested it on the bench. Now I need to make some additional cables to take the test outside. This proved to be a bit of a challenge because I don't have the proper crimper for this job. You might be able to see me improvising in this clip, but because of the crimper situation, I had a bit of a problem with wires pulling out from the connectors. So I've got the cable repaired. Seems to be alright, seems to be holding. But I ended up chewing up my only spare connector, so if I mess up another one, I'm going to have to get more. Alright, let's get all this stuff put together out in the field. right, here we go. Now, boop. Still got no signal from the PV. All right. In the negative hole, 200 volts, 20.2. Okay, so we are hot at the mouth. All right, well, we've got 20 volts coming out of the solar system, and we're only reading 2 volts in the charge controller. So I'm going to dick around, look around in there, and see what I can find. So the photovoltaic is indicating 2 volts at the terminals. Now, I've measured the panels themselves, and all told, I'm getting about 20 volts, a little bit more coming out of that. And I've tested continuity between all of the cables, and it seems to be coming through just fine, so I have no idea why that's indicating 2 volts. Damn it. I couldn't get all the parts working together in time. Hopefully I can get whatever was wrong resolved before the next installment, and we can move forward from there. The next thing that needs to happen is the building of the shelter where the solar panels are going to get mounted, and the designing and building of the enclosure to protect all this gear from the dust and the rain. Anyway, thanks for stopping by the hangar. Tune in 2 weeks to see the continuation of this project, and hit like and subscribe, and I'll keep making more projects like this for you to see. And always keep hacking.